So now we are ready to finally explain how to do a surface integral. A surface integral is nothing else than doing a double integral over a surface that isn't flat, okay? In the previous chapter, you learned about double integrals, and you first started doing a double integral in a rectangular area, and later I showed you how to do double integrals in a non-rectangular area. But it was always an area defined on a flat plane, right? For example, the xy axis, and you had some functions that were the limits of this area. But now we want to do a double integral on some surface which is curved like this. So it's a surface that exists in three-dimensional space. So how do we do it? So say, for instance, that you want to calculate this integral. The double integral along the surface S, which represents a curved surface, of some function, and this function usually is written in terms of the two parameters of the surface S, okay? So if this was the surface S, you have the two parameters, u and v, right? So the function that you're integrating can be different at every point in the surface. So this is a function of u and v, ds, the differential of the surface. So how do you integrate this? And the answer actually is quite simple. Just consider that the three-dimensional space is mapped point to point. For example, this point is mapped into a certain point in the two-dimensional parameter space, okay? So here in parameter space, which is an imaginary construct that we can have in our minds, we have the parameters u and v, and we have this mesh, which is made up of constant intervals in u and v, yeah? So now each point in parameter space is associated to a certain point in real space, okay? So what we do is, we do the integral on this parameter space, on the u and v plane, and therefore this is a flat domain, so we can apply everything that we learned in the previous chapter. And the only thing that we need to take into account is that ds is going to be squashed or stretched with respect to du dv, which would be the differential of area in the parameter space. In other words, we can do this double integral, which is a surface integral, as an integral in u and v. So we could have u1, u2, v1, v2, and actually in the most general case, this would be a non-rectangular area in the uv plane. So this could be u1 as a function of v and u2 as a function of v, right? So this is a non-rectangular area of the function of u and v. And then ds is simply some function g of uv times du times dv, such that all of this is actually ds, okay? So this function g of uv, which I will teach you how to calculate, is telling us how the area in the parameter space, which is du times dv, which is this red area highlighted here, how is that area squashed or stretched in real space, okay? Because depending on which square we choose, the area is going to be different. For example, this area here in parameter space has the same size as this area here, so they have the same size. But if you go to the corresponding area in real space, it's obvious that this one is stretched compared to this one, yeah? So this factor, which depends on where we are, it depends on u and v, will take into account that stretching or that compression of ds, okay? But at the end of the day, the only important thing to notice is that we are calculating a surface integral on a curved surface simply as using the same method of calculating a double integral, with the only difference that we are adding this factor that is like a stretching or scaling factor. This should remind you very closely to what happened when we changed coordinates, for example, to integrate in polar coordinates, right? Where we had dA, and it was d rho times d theta times some factor, which we found is equal to rho. So that would be actually an analogous situation, because actually a change of coordinates can also be seen as a parametric surface, So this general case of parametric surfaces is a more general case of which the change of coordinates is a specific case. Okay? Don't worry if that sounded too mysterious. You will understand it with examples. So the question now is, how do we find ds? And I'm going to show you three methods. The first method is by using geometrical intuition. The second method is by looking it up on a table for very common, if a common surface is used. And the third method is by following a recipe. And as a spoiler, I can write here what the recipe is. So this is the norm of the normal vector. You remember I showed you how to calculate the normal vector using the partial derivatives. So you calculate the norm of that normal vector times du times dv. Okay, so these are the three methods, and I'm going to give you a video for each of them. So see you in the next video.